How we do, guys?
Not well.
Let's see. Residents, windshield wiper this pipeline over, yeah, cation here. The lone pair can move in here, residence area, another residence structure. We've delocalized the charge. The cation has been delocalized. Questions?
Why, I know that you said not to make like the oxygen not have an octet. Why can we do that to nitrogen?
Nitrogen has an octet. 2, 4, 6, 8. Yes. The one on the end is most basic, most electron rich, and this would be most basic, most reactive. Lone pair is not conjugated. In these, the lone pair is conjugated. Yeah? Conjugation is going to move the the lone pair. We can place it on other carbons or other atoms of the other carbons. Actually, you can place, of these three, which is most basic? Of those three, which is most basic?
Not number one. I don't know, I didn't work number.
You should be able to determine which of these three is most basic. One of them is more basic than the other two. Comes from doing resonance structure. That's exactly what one of the problems was in the resonance packet, I believe. Anytime you do problems, you got to make sure you figure out what are you learning from the problem. It's the same problem. Question?
I thought, like, in the example, what we did in the resonance packet, the lone pair is able to go to the oxygen. Is that, I don't understand how that's connected to basicity.
Did I say it wrong? I said one of these is more basic than the others, than the other two. Yes.
No, I'm saying like, why is it that answer? Because
Well, if you can move the lone pairs somewhere else,
then it's
that means the lone
electron
pair is
rich,
spread out.
right?
What?
Then it's electron rich.
No, the electron poor.
Okay, well, you said problem. That's all.
What did I say?
In the packet, you said if it moved, was able to delocalize the lone pair, all like for this instant, all the way to the oxygen. It was electron rich.
I wrote that or said it in a statement? I don't remember saying that.
You said it, but I'll correct
No, delocalization spreads the electrons out. I mean, if we move these electrons somewhere else, there's less electrons on the nitrogen. You can't do that here. You can't move these electrons anywhere. So there's more electron density on the nitrogen. Here, the electrons are moved. On the far right, how we do? No, we're doing heat. You get the most stable product. These are the two. We excluded these because we're going to react with this pi bond. You've got to figure that out first. And then because of heat, we get the more stable. Which is more stable, the one on the far right or far left? The one on the far right, it's tri-substituted alkene.
I thought you said we wanted to make the cation the most stable carbon.
We did. Yes. You make the most stable carbocation.
But can't you do an alkyl shift? And put it on the
Not going to be
tertiary?
any alkyl shift. React here, I did it here. Get cation here. That's secondary.
Yeah.
When I do resonance, I get a tertiary. Okay? So my cation has secondary and tertiary characteristics.
So chlorine bonds there, right?
Why the chlorine bond where?
Where you put your cation?
The chlorine bond's here.
No, where you put your cation on the other resonance structure?
doesn't bond there?
Why would it bond there? We got heat, you get the most stable product.
But you said it goes to the most stable carbon cation, right?
This is the same cation. These are not different. It's a hybrid. It's only one cation. It's got characteristics of both of these. With heat, you get the most stable product, right? More stable product is going to come from attacking right here, because it gives this product, trisubstituted alkene, more stable than a di. That's how we determine stability.
Why would you just make the tertiary carbon first to be the left side? Using the right one.
By attacking H plus like this.
Yes.
Yeah.
Okay.
Sounds like everybody does.
Attack here, make H here, plus here.
And then,
It's tertiary. Then what?
We all focus on
But
the
which is
cation,
better?
not the alkene.
A tertiary cation with no resonance, or a tertiary cation that has resonance? See, this tertiary cation has resonance.
So what do you want to put at that tertiary cation because it still has resonance?
It's not. It's about the alkene, right, Dr. Stevens? Not the cation.
There's two different statements here. The stability is about the alkene, which is more stable, di or tri?
Try.
Tri.
We all focus on the cation, not the alkene.
Okay?
But I thought with heat it was a 1,4.
No. In the model example it was, but I told you, you gotta be careful. I said it several times. It always 1,4. It's the most stable. Now, if you look at some of the problems that I gave you the key, a couple of those were like this. The 1,2 was actually the more stable. Okay, if we go with that cation, that's the product. What about this cation? You said, why not make this one? Where's the resonance of this? Which is better, a tertiary with no resonance or a tertiary with resonance? Okay, problem is you don't get the tertiary until you do the resonance.
even though it's secondary with resonance, still wins.
But it's both secondary and tertiary. This one is, so tertiary is there, but it's also secondary by resonance. Tertiary here with nothing else. Resonance with tertiary or no resonance? Resonance better. Problem is you only see the tertiary after you do resonance. Doesn't mean it's not there at the beginning. As soon as it's formed. All this was in the other problems that I gave you the key. Problems. If something didn't make sense, ask questions. Don't ask questions, I assume all the answers made sense. Okay, we also made this statement. Whenever you make a cation, make sure it's allylic. That is next to the alkene. That's not allylic. Okay? You can't do resonance. So because you can't do this, these two products are out, if you look at it. Movement that way. Then, by the way, if you did this cold, what would be the product? No. Kinetic, fast. 1,2. Be the same product if you did it cold. Cold is always 1,2 because 1,2 is faster attack because it's there. Okay. 1,4 is slower. Heat gives the most stable. Which one's most stable on the end? One on the right. Questions? Yes.
Do you get a point for putting the first one?
Yeah.
Right.
I like to fight. And if you cross out the middle two.
I
crossed out
but I know they
We'll
weren't.
consider it. I didn't realize it was 2 points. Usually multiple choice on quizzes is 1 point.
Okay.
But maybe I made it 2 so I could get partial credit, or sometimes I even get half. Yeah, I mean, 1 is better than 2 and 3. At least you got the right cation. Okay, Gill's Alder. It's what we got here. This guy's the diene. Turn it, zip it together. 4 plus 2 is 6. You got an oxygen bridge. I drew that back in. These two groups are trans here. They're going to be trans here. You can do it either way. The other way would be the enantiomer. You can even show this here. Both bonds to oxygen have to be the same side. I'm not really worried about that. Mainly as you see that bridge there. How we doing? Forgot about the bridge?
Yeah, I forgot to add it back in.
You forgot to add it back in? Okay, a variety of cleavages here. We could do alpha cleavage about the carbonyl. Give, what's this called? A psyllium ion, yeah? You can do resonance of that. Resonance stabilize. Alpha cleavage, make cation next to a lone pair. You can also cleave on the other side. That was A. Cleave on the other side would give this acylium ion. You can also do alpha cleavage about the ether. Cleave here to give this cation, resonance stabilize. Or the other side, resonance stabilize. Actually, the resonance structure that you could draw for all of those would be major. These are actually the minor resonance structures.
Is it the McLafferty one? Is that there?
You can't do McLafferty with it there. McLafferty requires something. I don't think you can do McLafferty.
I thought it just forms a ring and somehow the O takes the H and...
Yeah, you cleave it, you get an enol. Yeah, but it requires a gamma hydrogen. That's what I asked you to read about. I think that's stated on the handout. It requires a gamma hydrogen. Okay, how do we do on that? Yeah.
So any of those, or just?
All you have to do is give one. Give one of the most likely. Like give one of the presidents from the 19th century. They thinking would work. You could have said that one too. Oh, R.B. Hayes.
Yeah, good old Arby.
What? Okay, he will be posted. Make sure you. Looks like we need a little looking back at diene 1214. Okay.
You can look back at everything. Rather.
There were a number of questions there. The answers are on the back. The key is in the back. It's upside down. I'd recommend working those again. Each one you work. Make sure you get the right answer to the key. If you get the right answer to the key, sounds like you know what you're doing. If you don't get the right answer to the key, sounds like you don't know what you're doing. If you don't know what you're doing, then you need to do further studying or asking questions. All right? This is sort of testing yourself. That's how you should be studying, right? Question?
Do you have any other off hours, like Monday or Tuesday morning? That's just this afternoon.
Monday at 8:30? Here? Okay, we'll be here 8:30 on Monday morning. Okay, let's get back at it. You have any questions about those 1, 2, 1, 4 addition reactions in the handout? Let me know. While we just did mass spec, let's pick up there. Mass spec. We left off here in the lab lecture. Three spectra. Which compound goes with the top spectrum? Anybody get that? Compound gives you assigned to the top spectrum. Anybody? All right, let's look at what we picked up here. We'll try again on Monday, the mass spec. Okay, summing it up. What type of nucleophile can participate in SN2? Strong ones. Actually, that statement can be reworded. SN2 requires a strong nucleophile. And we'll probably reword it and state that later. SN2 requires. Why does it require a strong nucleophile? Because the nucleophile is involved in the rate determining step. The nucleophile is not involved in the rate determining step in an SN1 reaction. Seemed like we left something off on the previous page. I thought that was where we were at. Yeah. Yeah, these over here. Rank these from weakest to strongest. Weakest to strongest. If I was to look at them, I'd probably want to pick out the strongest first. Probably change that. What's the strongest here in this series? Now, water's not the strongest because we have an O minus here, and we said that anion is stronger than neutral.
I might say S minus is stronger than minus.
What you got?
I was gonna say NaSH.
Uh-huh. Weakest, again, I would want to make this one, that'd be the strongest. Let's see. These are all anions, right? Get rid of the spectators, yeah? S minus, O minus, neutral, that's got to be the weakest, one. Let's do strongest and label it 4. What is this here? OAC.
Acetate.
Yes, you should have seen that in Gen Chem, right? Acetate. What is acetate? I like the charge on, yeah? Acetate, yeah? Okay. Compared to the other one, the other oxygen. Which one's stronger?
Acetate.
Hydroxide's stronger. Why? Why is acetate
It's got-
weaker?
Yeah, it's got resonance.
Because this is really not an anion. The anion is delocalized by resonance,
Yeah.
right? These down here fit the examples up there.
So if we're doing
What'd y'all work on last night?
Lab report.
I report. Okay, and also this,
No.
mass spec, answering these. I don't feel like, does anybody have these ranked in a series that I can look at and maybe we could, what do you know?
I did that, so the strongest.
Yeah, I wish it was strongest. Okay, acetate's weaker than this one. Which is stronger, S minus or O minus? S minus, why? Well, the example's up there because S is a worse parent. Oxygen's a better parent. This is 4, this is 3, this is 2, that's 1. 4 being the strongest one. Down here, which is the strongest one down here, number 2?
Strongest one I put as KNH2.
KNH2. Let's see if that ends up being the strongest one. They're all anions. They all have K. F minus, Cl minus. right? F minus, CO minus, O minus, O minus, N minus. Okay? Minus charge up there on all of them. I've got two oxygens. Let's compare them. Which is a stronger base? O methyl minus or O butyl? Tertiary butyl.
Butyl.
Which is a stronger base?
Butyl. Tert-butyl.
Actually, tert-butyl, why?
Because of the CH3s.
It's got all these rich friends. Okay? By the way, we did acid base back then. You might want to look at that handout again. All these things were described there as well. Hold on, we're not doing base. We're doing nucleophile. So my bad. Which is a stronger nucleophile?
It's the same. It's the same, right?
We're doing nucleophile.
But in
And
this-
it's not going to change up there for our answer. I may have been saying base up there. Nucleophile, which is stronger nucleophile?
it's still the one on the right.
Which one? No, this one. Terbutyl is not as good. Why?
Yes.
Sterics influence nucleophilic strength. Sterics is bad. But you got two oxygens, they're the same, O minus, but one has sterics.
No.
That's a better base, but it's a worse nucleophile. Sterics hurt nucleophilic strength. So OMe is stronger. Okay, which is stronger, O-methyl or NH2? Well, don't consider sterics unless like everything else is the same, because sterics is not a major thing, it's sort of secondary, but it's very important. OMe or NH2? That or NH2 minus? Well, this is the difference in not hybridization, but electronegativity. This is the difference in parent. Which is a better parent? Yeah, it holds its electrons tighter. It's not going to want to get out there and do backside attack. This is a better nucleophile. So that's better than this, but this is better than that. How about these?
Okay,
Oh, F minus.
That's an extremely good pair.
How does F minus compare to O minus? More electronegative, so it's a better, it holds it tighter, better parent. So that's going to be worse nucleophile than this. Okay, what about Cl minus comparatively to maybe that guy? Which is better nucleophile?
Yeah.
Fluor. No, it's the opposite. As far as
This could be a little bit counterintuitive.
no, is it Cl because it's bigger, so
Right, because
they're spread out.
It says iodine is better than fluorine.
Yes,
in
it's
that case,
Cl.
it's Cl better than
Yes, what did we say? Did we on that page, or are you looking
fluorine.
at?
It's on the page right before it.
because the electrons are farther away from the nucleus.
Where does it say that at an iodine?
Go back.
Right there, the page you're holding in your hand.
It's on the other.
Oh, okay. Yeah, Cl minus is a better nucleophile. I said it earlier. But there's some little counterintuitive. You can just say it's a worse parent. Counterintuitive because it looks like it's more stable. It is more stable, but it's also a better nucleophile. That's what's counterintuitive. Okay, so let's put numbers on those. Which was the strongest? We'll call that number 5. This guy was the strongest. What's next?
The O-methyl.
Yeah, that was next strongest. And this was a little bit weaker, 3. Still O minus. These guys are more electronegative. 2, 1. Yeah, I like that ranking. These anions are the conjugate bases of strong acids. You got to be careful of when you do comparing bases and nucleophiles. The main thing is with nucleophiles, sterics becomes important. Actually, F minus is a better base, but Cl minus is a better nucleophile. That doesn't really make sense for anything we said because there's really no sterics. The bigger it is, the better nucleophile it is typically. We haven't really defined that. So this is a little bit counterintuitive to me. The rest I think should make sense. We'll make a couple more statements later, I believe. Question here?
Oh, I was gonna ask, will it always be the case, like, if you're comparing, like, ions or anions with, like, ones with oxygen and nitrogen, will the oxygen and nitrogen ones always be stronger?
I'm not sure what you're asking, but
Like, would it ever be?
I mean, we said that the anions are more nucleophilic than neutral. That's more nucleophilic than this. That's more nucleophilic than this. If you start going an anion of an oxygen versus a neutral nitrogen, now you're doing apples and oranges and it can become a little difficult.
Oh, I meant for, like, this example, like, if you had oxygen to butyl and chlorine, will chlorine ever be more nucleophilic than, like,
Chloride.
yeah? No.
No, chloride, your halogens, there's a little vagueness there. For example, I minus is an excellent nucleophile. We'll try to summarize this again as we go forward. A lot of times the questions are meant to see what type of questions that come out of the question. So questions are coming up. We may not be able to answer them all right now, but please write them down and let's try to get them answered. Or we may never really answer them because they may be difficult to answer because they're kind of counterintuitive. And we need an explanation that we're not ever going to discuss here. Because at some point we have to sort of draw a line between what we're going to discuss here and then what may be discussed in an advanced course. Question?
Yesterday you said stronger bases or stronger nucleophiles. Is the only case that's not true of sterics anymore?
Typically, strong base correlates with strong nucleophile unless you start getting sterics. For example, the tertiary is just good strong base, but it's a lousy nucleophile
So you won't,
because of sterics.
you won't give us one like the F minus and the Cl minus, just because, like on the test you wouldn't do that. Because that doesn't have to be sterics.
Larger, well, I don't want to give you a definitive answer because it depends on the question. And maybe I give you a certain question that I expect you to be able to handle, but because maybe I supply you with some information or something. Then you would say, well, you said you wouldn't ask this. Well, I didn't really ask it in the way you might have thought I was going to ask it. So let's just keep at it. More strong nucleophiles. Which compounds have lower strong nucleophiles?
NA.
I see 3 of them. KCN? Yes. Why? Forget about that. This is what? Cyanide. Potassium cyanide. What's strong? What's a strong nucleophile? Same as a strong base. Anions? sp3, sp2 nitrogens. But then you got sterics influences that. Also, there are exceptions. Not every anion is a strong nucleophile. For example, F minus is really not a strong nucleophile. It's so electronegative that it holds its electrons tight. So there are exceptions. But that's the starting point. Anions. Let's see if that serves us well here. Well, that's an anion. reaction. Strong unless we have a reason to say it's not strong. And we know the charge is on carbon, right? We know Lewis structure.
Third.
The NH2.
Right here. This is O minus, right? And the methyl is not very sterically hindering. It's a strong nucleophile. Any others?
Yeah, the NH.
Propanol, strong? Not an anion, not an sp3, sp2 nitrogen. So it's not one of those. Why would you classify it as strong? Any reason to classify it as strong? No. How about this guy, this acetic acid?
No.
No. How about this one?
Yes.
Yeah, that's an sp3 lone pair nitrogen. So even though it's neutral, that's a pretty strong nucleophile. Now you might say, is hysterics? Well, hold on. It's a primary amine. I can make it a lot worse. I could put 3 more groups on the nitrogen, maybe put some groups here. Now it's got a lot of sterics. So just one group is not going to sort of make it. Primary amine is not really sterically hindered. Those 3. How about the next amine?
It'll be a weak.
Aniline.
Weak.
No, this lone pair is in what type of orbital? The orbital. That's conjugated. We showed examples of conjugation is going to make the lone pair be spread out.
But it'll still be a weak one.
Less electron rich. Nitrogen really doesn't have as many electrons as it looks like it does. Electrons are spread out. I see only 3 strong ones up there. Water, weak. SN2 requires a strong nucleophile. So if you were trying to do an SN2 with this, are you going to be good, have a good reaction? No, that's a weak nucleophile. You don't do SN2 with the 3 we circled, really. SN1? Yes, SN1, any type of nucleophile is good with SN1 because the nucleophile is involved in the fast step, which is the easy step. SN2, it's the rate determining step, which is the difficult step. Okay, we're going to look at some various examples of SN2. Some specific examples. Some of them have like maybe even names, like a person's name, and some terminology. So what are we doing here? First, alkylation of oxygen. Putting an alkyl group on an oxygen. Let's look at this. Is this a good nucleophile for SN2? No, just like that. No, it's weak. Can we make it a strong nucleophile? Yes. If we can remove the H and make the anion, now it's a strong nucleophile. Now how strong? Well, not that strong. It's resonance stabilized. But it's still an anion. And it's strong enough that we can do the chemistry. Can we remove this H? Sure, that's a carboxylic acid. How can you remove the H?
The base.
Reacted with base. What's your favorite base?
I don't really have
How
one.
about KOH? What would KOH do to this acid? That's acidic. You got hydroxide, right? These electrons take the H. Let's put in a bond, and that bond moves there. We get this plus what? Plus water. Where's the K plus sit? With the minus. I mean, the K plus just always sits with minuses. It's spectator ion. So we can make the better base by deprotonating the carboxylic acid. Now we can come in here with some type of carbon with a leaving group, and we can envision a reaction. Now the nucleophile can come in here and boom, do an SN2, kick it off. The oxygen is now bonded to the ethyl. We just made that bond. And what if we put on the oxygen in this process? There was an H, but now there's an alkyl group. So we alkylated the carboxylic acid by an SN2. But we first had to make the nucleophile, make this a good nucleophile. Okay? By the way, what type of compound did we make? Started as a carboxylic acid. We now have a ester. You know? If we totally balance this out, we make water. What else do we kind of make if we want to show a discrete compound here? KBr, right? Because we got a K plus, and then that Br minus that get kicked off. Those are ions. They may just remain dissolved in ionic form. We can show it as KBr. Okay. What about the next one? What about an alcohol? By the way, what's the pKa of a carboxylic acid?
15, 16.
About 4 to 5. Okay. Alcohol is not as acidic. It has a pKa of about 16, like water. You cannot deprotonate an alcohol with sodium hydroxide. By the way, if we review our equilibrium knowledge, back down here, first was an acid-base reaction. This has a pKa of about 5. What's the acid on this side of the equilibrium? Water, 16. Which side's favored, 5 or 16? 16. Yes. It's highly favored by 10 to the 11. KOH is strong enough to form this in a good amount, huge amount. But down here, if you react hydroxide with this, you make that plus water, 16 and 16, which side's favored? Neither side's favored. And if neither side's favored, it's just, in practice, ain't going to work for you. I feel like you guys just don't know what I showed here. That's an O minus, right? And sodium plus. Okay? You don't necessarily always have to show the charges. A lot of times they're just shown sitting there. But that's not covalent. That's ionic, right? Okay? So you can't use hydroxide, which is the most common base around, with alcohols. Instead, you have to use something else. For example, sodium. This is sodium metal. That's just pure sodium. Sodium metal. To use sodium metal, you can make this guy, but you also create hydrogen gas, H2. That's the fate of the H here. Now, this is a redox reaction. Redox reactions are often radical reactions. It's not an acid-base mechanism where we take the H, because if this took the H, you'd make NaH. But we're not doing that traditional acid-base chemistry. This is redox. Now you can balance this if you want. You've got 2 H's over there, so you really need 2 of these. You can balance it by putting 2 there, and 2 here. Now it's completely balanced. That looks a little ugly to me. By the way, what do we want to call this guy here? This is called an alcohol.
Alkoxy group.
Alkoxy is close. Alkoxy group if it was on something. It's an alkyl with an oxy, so it's alkoxy, yeah. But the oxygen is also a minus. What do you call Cl minus? Chloride. Alkoxide, yes, very good. Oxide makes sense because O, just O, like 2 minus is called oxide. This is an oxide with an alkyl group on it. Yes. And you could say the sodium alkoxide. Okay, if you take an alcohol and add some sodium metal to it, and we may do this in lab, although we could do it. So we don't have a lab on Monday, Tuesday, but we will have a lab lecture. Okay, we'll use some lecture time. Particularly UV Viz, which I sent you by email. You take an alcohol and drop in sodium metal, it'll start bubbling, giving off bubbles. Put a balloon on it, the balloon will inflate. What are the bubbles in the hydrogen gas? Then this will be just dissolved. You won't see that unless you remove. If you use excess, you won't see it. But if you remove the excess, then you'll see that in there as a solid. Otherwise, it'll usually stay dissolved. It's a redox reaction, not showing mechanisms. Okay? But this is how you typically make your alkoxide. So boom, you take this, sodium, the alkoxide. I mean, sodium is there with it. I showed it 2 different ways here. Now we can come in with a carbon with a leaving group. Now, boom, because now we got a good nucleophile. Boom, now we get the bond made by an SN2. And if you want to show some byproduct here, what else do we got? Sodium chloride. We also made hydrogen gas back over here. Right? Hydrogen gas was produced. By the way, how do you know it's a redox? We made sodium plus. What's the charge of the sodium here?
Neutral.
Neutral. It went from neutral to plus. It has lost an electron. So the sodium has been oxidized. If something is oxidized, that means something's also been reduced. What's been reduced? Actually, the H. I don't know if you did this in Gen Chem when it's covalent here. The H is considered +1 here, even though it's not actually an ion. It went from +1. What's the oxidation state of H in the elements? 0. So that went from +1 to 0. That's a reduction. So, redox. So, okay? Can't use sodium hydroxide with these non-acidic alcohols. What about phenols? Can you use sodium hydroxide with phenols? Why do you say yes? Because I didn't draw an X through the arrow?
No, because phenols are acidic.
Okay, how acidic? 10. Hydroxide can react to make this plus water. What is water? 16? Which side's favored? 10 or 16?
16.
16. By how much?
10 to the 6.
10 to the 6. 10 to the 6 is enough. Typically, 10 to the 2, 10 to the 3 is enough. This is enough. That is, phenols are acidic enough. And you should know why this is more acidic than that. Because the anion is resin stabilized. You can use hydroxide with phenols, carboxylic acids, but not regular alcohols. You have to use something more like sodium. That's traditional. There's a variety of other strong bases, but sodium is traditional. You can actually also use potassium. You know, other group 1 metals also work. So down here with phenol, sodium hydroxide makes the, what do you want to call this? It's not an alkoxide. It's the anion of phenol. Phenoxide. Yes, it's a sodium phenoxide. Let's get rid of this, okay? That's minus, right? And these electron, okay, methyl iodide. That's some very reactive stuff. Methyl iodide. Why is it so reactive towards SN2? Iodine is your best leaving group. Also, absolutely no sterics. Methyl iodide. Very reactive, very toxic. And we put a O-methyl to make that bond there. So we methylate our phenoxide. Plus what? Sodium iodide? Yeah. So in these examples, we have to first make the anion. Because we know we need a strong nucleophile for SN2. Making rings. you take this compound here and treat it with sodium metal, you can get this 5-membered ring with an oxygen plus sodium bromide. Can you envision what's going on here? What does sodium metal do to anything that you know? It makes the alcohol an alkoxide. So sodium metal makes this a minus, right? Plus hydrogen. Now can you envision how you get the ring? These electrons, let's do it up here, because there we can come in more. Boom. Kick that off. What does that get? Product, right? So this is just an example of, by the way, what type of reaction are we doing here? Did it have a name? Did we not mention the name?
SN2?
Yeah, but it's got a name. Did anybody pick up on the name on the other page?
Williamson ether?
Well, yeah, Williamson ether synthesis. Down here, because what type of products did we make down here? An ether. When you put another alkyl group on the oxygen, you now have an ether. What was made at the very bottom? An ether. When you do this with alcohols or phenols, make the anion and then alkylate and end up with ethers, it's typically called a Williamson ether synthesis. Apparently Williamson was the chemist that sort of did this a lot back in the 1800s. So terminology for this reaction up here could be an intramolecular Williamson ether synthesis. Intramolecular meaning, internal. And yes, it is an internal SN2 reaction. So, whenever we do synthesis, we can also consider going backwards. That is, what if you were given this ether here? Can you provide a Williamson ether synthesis of that compound? That is, how would you make that compound? Synthesis. Provide the starting materials and the reagents that would give that compound. What if someone wanted to buy this compound from you for $1 million a gram? That would be an amazing price for that. You'd be very eager, but you got to make it. How would you make it? Well, I see an ether. And ethers are commonly made by, guess what? The Williamson ether synthesis. And the Williamson ether synthesis starts with what type of molecule or compound? An alcohol or a phenol. Okay, so what alcohol would you like to start with? Then once you make the alkoxide, etc., you react it with something that has a leaving group. So that's what that was all about. So just with that knowledge, show what you would use here. There's theoretically two different approaches you can do here, but one would be better than the other. Somebody got synthesis? we're essentially going backwards. Coming forwards, we're making bonds. What bond are we going to make in our waves and ether synthesis? This bond here? No. What bond do we want to make? What bond did we make in our examples? We made an oxygen-carbon bond, right? So you want to make an oxygen-carbon bond here in this example. You have two choices, either that one or that one. Which one would you like to make? Well, let's do both. A, B. Backwards. When you go backwards, you use a double line arrow like this. This is a retrosynthesis arrow. We're going backwards. What if we go back from A? That would involve having the oxygen connected to everything over there. And the oxygen would be in the form of what? The OH, or it has to be minus, correct? Okay. If we had that, what would we react it with to give that over there? Just that? Would these two react to give that? That is, if we go forward, would these two react to give that? Why not? What's going to be the mechanism here? Doesn't have anything, it can attack a carbon, but it doesn't have anything. We're doing SN2, and SN2 doesn't involve carbon.
We don't have a leaving group.
Ah, you don't have a leaving group. You got an H here. Is H a good leaving group? No. Then what do you want to put here? How about a bromine? That's a good leaving group. How about that? Now, would this react? Can you envision a mechanism here?
Yes.
How would we form the A bond? These electrons coming in here and kicking that off?
Yes.
Would, okay. Well, what if we form the B bond? What would that involve reacting? That would involve this reacting with what? Just propane?
No, you'd have to have a leaving group again.
What do you want to put here?
Either a bromine or
Well, your choice. Bromine. How about a tosylate? It's a good leaving group. Like this. Okay, would these two react to give that? Well, mechanistically, bam, why not? SN2. Both of these would theoretically give that. One's better than the other. Which one's better? And why? Which route would you say is best? Which route is best? You could argue against what the answer I'm going to tell you, but I'm looking here. The bromine is on a secondary carbon. Here the bromine's on a primary carbon. Remember we did rates? What if we had a bromine on a tertiary carbon? What do we say about these? And we said it with exclamation points. There's probably 5 exclamation points beside this statement on a couple pages back. Never do SN2 with tertiary. Too sterically hindered. Well, what about secondary? You can, but it's not. Primary's better. Primary's better. This is better. Thing with your leaving group has less sterics. Now, the thing you could argue is, well, over here I got more substitution next to the nucleophile because that's the secondary carbon, but over here it's the primary carbon. Yeah, but it's really removed from the nucleophile. It's not on the nucleophile. The more important thing is we want to look at the thing with the leaving group. That's sort of the first thing to look one on the right would be your better approach of the two theoretically possible. Okay, this is synthesis. What bonds can I make? I mean, I don't know how you would make this bond. It'd be very difficult. There's no chemistry there. SN2 involves what? A nucleophile and something with a leaving group. That's why we showed it. Nucleophile is something with a leaving group. Now let's show the synthesis. Now this is sort of just retro. I'm going to show the synthesis all in one shot so we can go back to line reactions like we showed earlier in a handout. What if I take this compound here, which is called cyclohexanol? What do you want to react it with first?
Sodium.
Sodium, very good. You got your lucky shirt on today. You're in a good roll. Why sodium? Because we got to make the anion first. Then we come in with what? Maybe 1 bromopropane. And now we can show it in a clean. Remember how we said that this is 2 separate steps. 1, then 2. Not combined. Because if you combine these, sodium will react with this by a different reaction. 2 separate steps, but we can show that. Boom, there you go. There's a nice clean line reaction, multi-step line reaction. This was our retrosynthetic analysis. Retrosynthesis arrows. When you get into organic 2, you'll do more retrosynthesis. Alkylation of sulfur. Because up top we were doing alkylation of oxygen. Well, sulfur, I often mention it here because it's relevant to the body. Your body uses sulfur for a variety of things instead of oxygen. Sulfur being right below oxygen. So it's similar bonding and all, but it's just, it's a better nucleophile because it's a worse parent. Your body uses glutathione as a nucleophile, and the nucleophile is right here. Even in the neutral form, sodium's a pretty good nucleophile, which kind of goes against our statement of strong nucleophiles. It's not an anion, it's not a nitrogen sp3, so I'm telling you it's sort of an exception. It's a decent nucleophile. And in certain cases, this can become S- in the body. And then it's certainly a good nucleophile. Your body uses that often as nucleophile. You can read what's here. We said something like methyl iodide is toxic. You don't want to breathe or ingest this stuff. Why? Because your DNA or your proteins or something will start coming in here and doing all this, and you start reacting with your biomolecules and it's going to cause problems. Your body uses glutathione as a defense mechanism. It's around. Its purpose is to seek these things out, and this good nucleophile comes in here and does it instead and keeps this from happening. There's that good sulfur nucleophile. Again, in some cases, this may actually be the anion. Mucomist is given when you have a patient that is overdosed on Tylenol. Because Tylenol forms a reactive species that reacts with nucleophiles, particularly in your liver. It will ruin your liver because proteins in your liver react with the reactive species there. We give this because the sulfur goes in and reacts with the reactive species and protects your liver. Sulfur is a good nucleophile. That's just a couple of biological applications. We didn't actually show pure reactions. Most all that is just analogous to the oxygen. What about nitrogen? We can alkylate nitrogens, but there is a potential problem with nitrogens. For example, we could take this carbon with a leaving group, react with ammonia. It's a good nucleophile. These electrons could come in here and kick that off. That would give this. Now this is a salt. Because we used a neutral nucleophile, it has to lose a proton to go neutral. One could take the proton. Good division Br minus taking a proton and getting this. It's a standard acid-base mechanism. That's how you get a neutral molecule. But is the reaction really going to go that way? That's an acid-base. How do we judge it? Equilibrium. If I tell you the pKa of this is 10, what's the acid over here? HBr. It's like -5. It's a strong acid. Which side's favored? 10 or -5? 10. So is it going to the right? No. It mainly exists like this. That is, you're not going to remove the proton unless you include a stronger base. That's why if you look back on the first page again, here we have a nitrogen acting as a nucleophile, kicking off, it's like a tosylate, and we're making this. It's got that H there. Okay, we get this. Tosylate, just like Br minus, is not strong enough to remove the H. Well, why do you think they include potassium carbonate, which is a base? It's there to remove the H. Okay? Because the tosylate won't remove it. The Br minus in our current example won't remove it. All right? Now, the alkylation of nitrogens like this actually are problematic. And you can end up with putting multiple alkyl groups on your nitrogen. Now we have 2 alkyl groups. How does this happen? Well, there is something in this reaction that can remove the H. That is ammonia. Once it starts forming, ammonia can come over here and take an H from that. And you would get the neutral, but then you would also make ammonium, because ammonia took the H. But look at this. Once this is neutral, it's now a nucleophile again. And it can come in here and react again. And give an intermediate, but once you take the H from that intermediate, you can get this. This can actually keep going, because this can come in here and do it again. And even though you're trying to just put one alkyl group on, you can end up with multiple, or polyalkylation. This is a typical problem with nitrogens. Because in the neutral form, they're good nucleophiles, and so they react again. How do you get it in the neutral form? Well, I showed you. Not from the Br minus taking it, but the ammonia can. You understand this? This reaction goes 10%. You can't tell ammonia, hey ammonia, I only want you to react here. Once this is formed, do not go over there and take the H. The ammonia won't listen to you. It starts going over here, and you get all this in equilibrium, and you end up with this in your product. Polyalkylation. That's a problem. There's multiple ways to indirectly alkylate nitrogens. Organic 2, you'll see other ways. One way here will show and introduce a new nucleophile. Instead of using like an amine, we can use azide, which may be kind of new. What's the charge of the N3, the total charge of N3? You don't have to look up here. Look right here, the answer is right here. What's the charge of the N3?
Minus.
How do you know it's minus? Because sodium is positive. All right? All right, that's positive. The whole thing over there is minus. Now, what atom is minus? Well, it's 3 nitrogen, so it's got to be a nitrogen. Actually, azide was on the Lewis structure problem set from 3 weeks ago. 3 or 4 weeks ago. Azide. It's called azide. The Lewis structure looks like this. 2 on the end are actually going to be minus, the one in the middle positive for a net minus charge. Either one on the end, though, is your nucleophile. So these electrons come in here, kick that off, and we make this bond. Now you have the 3 nitrogens bonded to the carbon. I didn't show the full Lewis structure there. You can. And you can get this in good yield. Because at this point it's no longer nucleophilic. It doesn't react again. Now you can do an interesting reaction with hydrogen and a metal catalyst, and you can cleave 2 of the nitrogens off, and you can get a good yield of that amine. Where on the previous page we didn't get a good yield. We ended up with polyalkylation. Here you don't get polyalkylation. I'm not quite sure what the fate of the other 2 nitrogens is. It may be nitrogen gas, or it may be something that's reduced. We don't really need to worry about that. So this is a indirect method. We didn't make this by directly having like ammonia making the bond. We had sort of a surrogate making the bond. Azide. One of the first things is just to see that the azide is able to do SN2. Okay. Azide's a good nucleophile, right? It's an anion. Okay, with nitrogens we can introduce the idea of a quat. Quaternary ammonium compound. You ever heard of a quat? Some of you have like antibacterial gel or something, or liquids you carry around or you use. It's often just alcohol, but sometimes it contains a quat. If you go to the Y over here on all the extension area, on the wall they have a big box with a hand lever, and you pull and you get some gel and clean. That's a quat. If you look on, if you read the label, it'll say the chemical name there. I've seen it. I've been over there. Quaternary ammonium bromide or chloride. Those things are often used as antibacterials. Okay, what's a quat? Well, it's short for quaternary. Primary, secondary, tertiary. Quaternary. It's a nitrogen bonded to how many carbons? 4. Isn't it amazing how you can figure that out? Okay, here we go. And if it's bonded to 4 carbons, it's going to have a positive charge. Right? That's a quaternary ammonium compound, often just called a quat, for slang short. How do you make quats? Well, how about this way? Does this theoretically work? What if these electrons came in here and did an SN2? What would that give? That. So the nitrogen has Br minus. The nitrogen can't lose an H. Well, Br minus wouldn't take it anyway. But even if you added a base, it can't. So if you just do this and then like remove solvent or something that would be solvent, you would just have this. Since it's ionic, it would probably be a solid. Now you can take that solid and dissolve it in a gel and get your gel, lotion or whatever. There you go. So this is the idea of a quat. Oh, by the way, this is the one that's over in the at the YMCA. Read the label next time, if you ever go over there. You ever go over there and, anybody exercise over there or anything? Y'all exercise any?
We have a free gym that we pay for our school days.
What, down on the hill? Okay, good. Do they have any antibacterial stuff down there?
They have like a little handle.
Okay.
Put your hand on it.
See if there's a label on it. So the one over the Y says that name right there. Okay? What's the name of this? Didecyl. What is that? Two 10-membered alkyls. Didecyl dimethyl. Ammonium chloride. Okay? It's a quad. In biochem, you'll see choline. Sometimes it'll have an acetyl group, and it's called acetylcholine. Instead of acetylcholine, a lot of people say acetylcholine. Okay? That's where this has an acetyl group. But it's got all of its constant with this, and you've got a quaternary ammonium over the other end. So when your biochem teacher says you got a quad here, then you know what you're talking about. Okay? Acetylcholine is a very important neurotransmitter. The world's record for most bitter compound. You ever seen the Chemistry World Record book?
No.
Fascinating book. Things like this in there. World's most bitter compound. World's most exotic recrystallization solvent. You know what it is? It's not hexane. It's not methanol, isopropanol. It's liquid lead. Who's recrystallizing something from liquid lead? But world record. Okay. Most bitter compound is this quaternary ammonium. Now the anion is not a simple halide, it's this benzoate. But every plus has a minus, right? And that compound is a salt. It's an ionic pair, just like sodium chloride is 2 ions. Well, that's 2 ions. Apparently it's quite bitter.
What do they mean bitter by they've actually tasted it?
Yeah.
Which means they've tasted all
Well, see,
the
you know, a
other
while
ones.
back, people weren't so scared to taste compounds. Sometimes the problem's like, they didn't wake up. they learned you can't taste. But when LSD was first made, back in the 1930s, the guy that made it sort of tried it a little bit. He didn't know what it was, but on his way home, he had quite an experience. And there's a discussion of that. And then he was like, interesting experience, and then people start trying more. But yeah, what's the use of it? They put it in some medicines. They put it in antifreeze, so pets won't drink it. Because antifreeze otherwise is actually kind of tasty apparently to pets, right? I had a cat that died, I think it drank some antifreeze. Okay? I think maybe someone set out some antifreeze across the street and to get rid of the cat. People will do that. But nowadays they put something like this in the antifreeze and the cat starts drinking it and it's like, I don't want to drink that. Too bitter. Okay? Or medicines. I don't know what else. Not medicines. You can read it. Keep children and pets from drinking antifreeze. Variety of uses for bitter compounds. Good uses. Probably don't want to cook with them or anything. Okay, can we alkylate other things? Can we do this chemistry with other things? What about carbon? Well, the answer is yes. Can we make a carbanion? Because just a plain carbon with all H's neutral is not a nucleophile. It doesn't even have a lone pair. Can we make a carbanion? Well, yeah, we did this during test 2. What's the most acidic H here?
The one on the right.
Terminal alkyne, remember that? Okay. You remember what type of base we used to remove that H?
Strong one.
It wasn't hydroxide, because with hydroxide the reaction actually goes reverse, and that's the minor element. What kind of base did we use here? There was 2 I showed you on the handout.
Oh, it was the lithium butyl.
N-butyl lithium, or the potassium amide, like sodium amide, like NH2. Okay, get rid of that. That's really minus, right? That's what we use. These electrons can take the H, leave these behind. I'll just call that as phenyl. Boom, boom. And now we have an anion here. Your book loves to use this base here. I don't like it because it's a terrible base in practice. There's also another reason, and maybe I'll show you that should be informative. But now we got a good nucleophile. It's an anion, it's lone pair. And now we can put in something and we can alkylate it. Maybe we react it with how about this? I'm sorry. Go ahead, you've already got it drawn. Keep using BR as leaving group. Is that the only leaving group?
No.
No. Tosylate. Okay, I should vary it, but maybe a tosylate. We talked about variety of leaving groups. So plus, let's kind of draw this like this. So we got that, and we got that on the reactant line. What's the product there? Oh, well, stereochemistry. That's a deuterium, D. Which is the leaving group? The bromine or the fancy H? Bromine, of course, right? These electrons come in here. Okay, backside is not always easy to show, but we show it on the board. Backside, kick that off. What's product going to be? SN2. Let's see. Boom. Making bond here to this carbon. And that carbon's got a D. The one we're making bond to has a D. And then it has the other two carbons. That carbon and the other two carbons. Okay. There's a D on this carbon, though, that this thing made a bond to. Here's the bond that was made. Used to be a bromine here, but now it's a, that there. You've got to draw the D. Boom, boom, boom. How do we want to draw this D? I don't know if that's right or not. Is that right?
Yeah, but still be.
Is that right, stereochemistry? What is the RS here? Everyone? S? That should be easy, guys. What's the RS here? R? Is that right?
For the triple bond, is it bonded, did you just say it was bonded to carbons?
Yeah, 3 carbons. What if I showed it like that? Is that right? Same thing. I wish I had shown it like this first, and then everybody would have said, but why is the D not converted to dashed? And I'd have said, what do you mean? Common mistake you guys make is you think that inversion bold goes to dash. It's not always inversion. I could have showed it like this and bold went to bold. You can draw the product however you want. Got to make sure that it's truly inverted. SN2 comes with inversion, right? Okay. Product below. What's the product of the reaction below? DMSO is a common solvent, polar solvent. It's likely on the solvent list I gave you in week 1. Dimethyl sulfoxide. KCN. Product there.
How did the methyl group get pushed back? Look at the stereochemistry. Because the bromine's the leaving group.
Yeah.
So would it be the same scenario as the last one? Where the CN comes in?
Okay. How does the CN come in? It's CN minus, right? Comes in here. Kicks that off. Okay. Now we showed a transition state. These two groups are pointed this way compared to the bromine. When the nucleophile comes in, they straighten up. And then the bond breaks off, they come this way.
Okay.
Well, hold on, not quite yet. Boop. Now the phenyl moves that way. The bromine was this way, so the nucleophile in the board, so the nucleophile came in that way from the board. You want to show it like this? Do you like this better?
No, I was just wondering how it got pushed.
Well, does this make more sense of what you were thinking?
No, it just confused me.
I thought that's what you were thinking.
No, I just didn't understand the difference between this example and the last example.
There's not really any difference. That is, I've got two structures on the board, but guess what? They're the same.
Okay.
So, you can draw it like this, or you can draw it like that. But that over there is more like we did with the transition state. The bromine is pointing that way, right? On the board. It's in the board, like that. So if it's pointing that way, how does the nucleophile come in? From over here. If it comes in from over here, that's why I've got it drawn in over there. Now what happens? It takes those groups, pushes them planar, transition state, and then it pushes them, I can't make my hand go that way, it makes them come this way as we make the bond. It came in. So this is more like the transition state everything. But guess what? This is carbon with nitrogen beats carbon with carbons. So this is 1, 2, 3. H in the back, so this is S. 1, 2, 3. It's R, but H is in the forward, so it's S. It's the same thing. However you want to show it. If your backbone doesn't change, you can just replace this with your nucleophile and switch that. That perhaps is a little trick. You need to figure out how you want to approach it and show, but it's going to be inversion. And again, this is more like the inversion I showed you. This is R. Inversion is going to go from R to S. Just make sure you draw your product S. Now, 99% of the time it will go R to S. I can show you a wicked example where R went to R even though it inverted. That's because 99% of the time, this is your high priority group, 1. Well, the new thing is also 1. If the new thing ended up being maybe 4, like maybe, what if the nucleophile was an H, and this was an H? Well, then it wouldn't be chiral. But if that was actually a low priority, you could actually go from R to R. That's a rare case. In most of the cases, you're going to go from R to S or S to R with inversion. So there we go. Remember the stereochemistry. Okay, let's look at this here. Triggering mechanism by regiochemistry. You take this compound here and heat it in ethanol. You can get these two products over here formed. What's going on here? Plus HBr for totally balanced reaction. I got a carbon with a leaving group. I recognize that. Ethanol, is that a strong nucleophile? No, it's not an anion, it's not an sp3, sp2 nitrogen. Not a strong nucleophile. Weak. So right off the bat, can we do SN2 here? I already know you can't do SN2. What other mechanism do you know?
SN1.
SN1. SN1 involves forming what intermediate? Carbocation. What are carbocations prone to doing? Rearranging. You see how you get 2 different products? It comes from rearrangement. This is an SN1. We see that because we're using a weak nucleophile, but we also see this rearrangement. You don't get rearrangement from the SN2 because there's no cation. So how do you get these products? Mechanism. What's the first step? Say. Yeah. Bromine just has to leave. What does that give? Carbocation plus Br minus. What do we call this process? Ionization, right? This looks a little odd to some of you. Can the bromine just leave? Just up and leave? Does that make sense? Well, what happens when you put HBr in water? The bromine leaves, and you get H plus and Br minus. Just leaves the H. Well, guess what? Things can just leave carbons. What type of solvent is best to promote this ionization? Does HBr ionize in hexane? It does not. Because it's going to ions, and hexane hates ions. But it ionizes in water. Why? Because water likes ions. Polar solvents promote ionization. Polar solvents promote ionization. We'll talk about solvents in a little bit. But we see the analogy here. Okay, here's our first step. How do you get the first product? Ethanol. Do we make this an anion?
No.
I don't know how you would do that. There's no base here. It's neutral, but we can use the neutral nucleophile. Bam. What does that give? Boom, 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 boom. Oxygen now bonded. There's an ethyl on the oxygen, and there's an H. One lone pair left. Positive charge. Some of you want to just make the H magically disappear.
We have a negative charge bromine in the system.
Well, I'm just saying, some of you at this point, your H just disappears. That's not a mechanism. This disappearing H's is not a mechanism. It's there. How do we get final product? What can take it? Br minus. Somebody said water? Well, where's the water at? There's actually no water in this reaction. So that's a time where water is not an answer. If we have water around, yes, water. But this takes the H, bonds to the H, these electrons stay behind, we get that there, plus we're making that HBr that we showed. Now actually you could have used ethanol to take the H, because ethanol is sort of like water. So that would have actually been okay too. Because in ethanol, HBr actually exists ionic. Okay, how do you get the second product?
A hydride sugar.
Ah, carbocations are prone to rearranging. So this could move over here. So that's the A pathway. Or we could do the B pathway, hydride shift. By the way, when you do hydride shift, you move the electrons, not the H. Some of you had like this on your test or something. And that's not an appropriate error. The electrons move and the H is just attached to the electron. Okay? That's going to give, I'll draw it over here. Boom, 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 boom. Now the positive is there and the new H is over there. Now do you see how you get the other product? I'm not going to finish it up. It's the same way there. I'm just going to draw like that. There's a step or two there. Same way to finish it up. This reaction screams SN1. First off, weak nucleophile. You have to have a strong nucleophile for SN2. So that tells you cation chemistry. Also, the fact that we got regioisomers implies they had to have cation chemistry because you're only going to rearrange with cations. This is a classical example of an SN1 using a weak nucleophile. Ethanol is often a solvent. This is called a solvolysis reaction. Usually solvents are inert. They don't react by definition. Here it does, so it's really not a solvent per se. The solvent reactant is a solvolysis reaction. You typically just dissolve this in some ethanol and heat it up, and this will take place. So the reactant also serves as the solvent. Okay? What if we had stereochemistry in our products? I didn't show any stereochemistry up there. What if this had stereochemistry? What would the product stereochemistry look like? Please do that on your own. Remembering, if you have a cation, how do you attack the cation? Either side, right? Either side. So think about that. Show the same products, it's the same reaction, but just show stereochemistry with it. What is the rate equation for the above solvolysis reaction? Can you write the rate equation? Some type of constant times what?
This one is just going to be the bromine.
Alkyl bromide. Anything else in the rate equation? It's SN1. There's only one thing in the rate determining step. That's it. Does the concentration of the ethanol matter with the rate? No. Does not matter. What type of nucleophiles react strictly by SN1? Now we said earlier both, but we have to kind of clarify that. Theoretically they both can, but you're only going to give an SN1 with a weak nucleophile. Because if the nucleophile is strong, you're going to get, it's going to go SN2. Why? Does it have to go SN2 if it's strong?
Yes.
No, but it stays
Yeah, it's kind of, okay. Here's why though. Strong nucleophiles are bullies. They have to stick their nose in. Strong nucleophiles will not wait around for something to ionize. You got a bromine? You want to ionize? Well, too bad. Here I come. Boom, kick it off. The SN2 happens faster with strong. They're bullies. They're not going to wait around for ionization to take place. Strong is usually SN2 because they're bullies. SN2 also requires strong. So if you got a weak, by default, typically it's only SN1. Strong nucleophiles are bullies. They got to stick their nose in and become involved in the rate determining step. And they're also strong enough to do that. That's why they do it. Let's finish up this page here. Summing it all up. Here we go. I'll let you read the sum up because let's look over on the next page. We're about out of time. Please read the sum up. Here's some example questions with stereochemistry. The first one, one's reacting with water, one's reacting with hydroxide. Seems like a difference. Stereochemistry here. Look at these below. Okay, this is your mission for this weekend. This one here is going to be kind of interesting. That one's going to be interesting because what's happening here is, well, it looks like nothing should happen here, or neither, or I don't know. We got problems there. That's because what happens here is going to lead us into the next handout, which is what? Elimination. And we'll be hitting the ground running with elimination on Monday. And the elimination is our last handout for the test on Wednesday. 2:30 here today. 8:30 Monday.
Are you still meeting at 2:30 today?